I'm going to present our speaker today. Baldé is a co-founder and head of mathematical sciences at Zaiku Group. His activities sit at the intersection of pure mathematics, machine learning, quantum computing, and privacy-enhancing technologies. He develops advanced mathematics programs at Quantum Formalism Academy for students, researchers, and technology professionals, covering topics such as linear algebra, topology, group theory, Lie theory, and the mathematical foundations of quantum computing. He also leads the Quantum Formalism Substack, a community of more than 9,000 subscribers, including researchers, students, and professionals from academia and leading technology companies. So, Baldé, we are really thankful and happy to have you here. It's a real honor for you. Thank you very much. For us, pardon. I mean, it's a real honor for us.
For me as well.
sorry. So you can start whenever you feel ready. Thank you very much.
Yeah, I'll just find, I hope you can see the slides. Is it full screen?
Yeah, it is full screen. Thank you.
Okay. Yeah. So basically, for today, I just have two parts. The first part is two suggestions. I wanted to provide more, but I was looking at the time. I think 2 suggestions is more than enough, so that we can have at the end maybe 10-15 minutes where we can interact with the audience, ask questions, and have a discussion or something. So the first one, the idea that I will be sharing briefly is this thing of classical to quantum data encoding via geometric quantization. I think in this summer school, you probably encounter some of the basics, encoding schemes such as amplitude encoding and so on. So the second advice, or at least suggestion, is zero knowledge proof for quantum advantage. I think some of you also, you must have recently heard Google a couple of weeks ago. They came up with a result. Apparently, they can solve a discrete logarithm. I hear a bing. Is that a question or something?
No, go ahead. No questions at this moment. Go ahead.
Okay. Yeah, sorry. It's just I heard a notification. I thought someone was asking. Yeah, so the second part is really some career advice, mostly from my perspective here in Europe, in the UK. So that's why I call it the unsolicited career advice for those who want to get into industry, in particular to find career in Europe, UK, and EU in particular, because I have a good knowledge of the landscape, the industry landscape in Europe, but I also think it also applies to the US, the big, basically the developed countries. Okay, so let me get started. Oh, I'm trying to play next. Let's see. Okay, can you see this? This is a poster-like thing that I generated using my agent. Can you see this, the full poster?
Yes, we can see the poster.
Yeah, so before we go to the idea of classical to quantum data encoding, I just want to give you some overview about classical data. In particular, if you are interested in stuff like machine learning or even emerging topics in machine learning, such as geometric deep learning. Complex data, stuff like images, time series, molecules, networks, and all these things, they naturally have very rich mathematical structures that very often, especially if you do traditional stuff, like traditional machine learning, these structures are not, these rich structures are most of times are not captured in your model development. So being able to capture this is very, very, very important. because these type of data sets, they don't really live in like a flat Euclidean space. As I was saying, very often in the case of geometric deep learning, for example, you deal with stuff like manifolds, for instance. So that's the starting point here, that in many applications, data is best viewed, for example, as a signal on a certain domain, but that domain might have like a very rich structure that's often not captured in traditional machine learning practice. So this brings me to an idea that I'm really excited about, this thing of trying to leverage geometric quantization for classical quantum data encodings. For those of you in physics, you're probably familiar with this, especially those of you coming from a mathematical physics background. So geometric quantization in a nutshell is basically this idea of being able to quantize classical systems. In the case, to be more precise, generally you can imagine the classical system being on a symplectic manifold. So the idea is to use, to go from the symplectic manifold to construct the correct type of Hilbert space and the operators, and the corresponding notions that you have in classical to corresponding quantum counterparts. For example, you're in classical, speaking about symplectic manifolds, in classical Hamiltonian mechanics, you have the Poisson bracket. Then you need a construction that enables you to go, so you can construct, the traditional commutator of operators in quantum. So the idea is really to use the reach. So you imagine like classical data sits on a symplectic manifold, and then explore some ideas from geometric quantizations in order to do your embeddings in quantum states. So this really basically enables you to have some sort of geometry-aware type of encoding that takes into account, the constraints and all the other key intrinsic properties of your data sets, and takes them with them through this the quantization method. So this is something that we at the Zaiku Group we are actively working on this, and not many people, as far as I know, are exploring this type of ideas. I haven't seen much of it on the thing, at least in the quantum computing context, in the context of embeddings. So yeah, this is idea one. We can come back to this later. I added here some note as well here. The difference between the naive canonical quantization versus the rigorous. Okay, the second thing is zero knowledge proofs. This is generally something that often is associated with the, yeah, I hear a bell. I guess is someone coming, or is?
Joe, go ahead, Bambordé.
Yeah. So the other idea that I think is really interesting from an industry research point of view is the application of zero knowledge proof into quantum computing. I'll come to that in a minute. But traditionally, this thing mostly gained popularity in the blockchain industry. So this basically this idea of being able to prove a property, without actually, without disclosing sensitive parts of that. So for example, you can imagine you want to do a transaction, on the blockchain, for example, a peer-to-peer transaction between you and someone else. You are buying something from them. Well, it would be nice for them to know that you have enough balance, right? You have enough money to be able to pay, and that the transaction will go through, or it went through. and these things without revealing a lot of the details for privacy reason. So that's how zero knowledge proof really started to become popular in the context of crypto use cases. As I was mentioning during the introduction, Google recently did this. They use zero knowledge proof to show that they could find they have a better algorithm for solving the discrete logarithm problem. But they didn't disclose their construction. They kept it secret because, for national security, they say. Later on, some other people were able, some other cryptographers, very clever guys, they were able to actually build better algorithms than the better things than improved thing than what Google did. But yeah, you can see how this can be useful, especially in the context of national security. But I think it actually goes beyond national security. For example, very often we hear about companies or research groups or something making claims, or they have a quantum advantage. They have this algorithm that is this X, Y, Z, but they don't share. They only share the results. How do we verify that whatever the claim that they make on the paper is true? Whatever the algorithm or the secret algorithm that they have is true. So this is where I think Google's use of zero knowledge proof is basically a catalyst. I see this to be like going forward, especially in the context of national security and these things. Zero knowledge proof will be used a lot. There will be a need for building protocols to enable, for example, quantum hardware providers, to prove that their hardware has certain properties or whatever, they, performance and this and that, they don't share.
Bambordé, we suddenly stopped listening to you. Okay, let's wait for a couple of minutes.
To how they did whatever, buying or public sector or government, buying work is a stable connection. Can you hear me now?
Yeah,
Okay.
We can hear you now. You can repeat in the last minute and we will be on time.
Can you hear me?
Yeah, now we can hear you perfectly. Bueno, una disculpa, el lugar en el que está Bambordé tiene algunos problemitas de conexión. Ya nos lo había comentado previamente a la conferencia. Entonces vamos a esperar un segundo en lo que se vuelve a conectar y volvemos a retomar de donde se quedó.
Okay, sorry for this. I will just 1 minute. I will just move the router again upstairs for 1 minute. I will be back.
Okay, no problem. Ok, bueno, pues revisen sus notas.
This is better. Let's see.
Okay.
So at what point you stop listening to me?
Yeah, we will let you know.
I think in the very last slide, I think now we listen about 2 or 3 minutes of the last poster that you showed.
Okay. Was there an issue when I was going through the geometric quantization thing? No.
Oh no, that was fine. No,
Okay.
no. The second part of the verification problem. Yeah.
Okay. Yeah. Sorry for this.
Yes. Yes.
I was praying for the gods to. Yeah. So this part here, I guess, I was just saying, the origins of zero knowledge proof, how they became popular, in the use of in thing like in blockchain, for instance, being able to, for two parties, for example, to prove um, whatever, like say, for example, a balance from one person, for example, without revealing exactly what, and so on. So in the context of quantum, I also mentioned, I think this is also something that you are aware, that Google, a couple of weeks ago or a month ago or so, they said they found a better algorithm for solving the discrete logarithm problem, but they didn't disclose the actual circuit construction and the details. Yeah. However, they use zero knowledge proof to try to prove that they actually have the construction, which is amazing. And for me, the reason why I think this will be very interesting is that going forward, this will be very popular in order to prove, say, an algorithm does something, say, does a quantum advantage, for example, without actually revealing what the algorithm is. Likewise for the quantum hardware providers, to be able to say, we've done these, our hardware is able to do X, Y, Z, without putting too much information for their competitors to be able to see. So this is definitely something that I think for those of you, especially the young people looking to get into industry, I think this will be a very interesting research area that industry will be going forward. So that's why I said Google's work is actually a catalyst for that. And we're already seeing interesting stuff with this. Yeah. Just as a side note, we at the QF Academy, we put a use case on zero knowledge proofs for the National Quantum Computing Center, and it's been selected because many of the panelists for the hackathon thought it's very interesting. So we will be going to a hackathon exactly on the use of zero knowledge proofs. Okay, so that's it for this part. I'm just trying to say as much as I can before, just to make sure that the connection doesn't cut. And I'm sure we lost a few minutes, but we can come back to this again at the end in the questions if anybody has any questions. Can I proceed?
Yes, please go ahead.
Okay. I'm also learning how to use Zoom because I haven't used it for some time because to get rid of the panels so I can see my slides. How do I do this? Okay, this is okay now. Yeah, I minimize it. Okay, so the second part is, before that, I will just make a disclaimer. This is my personal opinion, and this is mostly based from my own experience here in the in Europe and in the UK. And this is mostly also for people who want a career into the industry, into this new quantum computing industry. So the first thing that I want to share with you is do some sort of a reality check. Can you hear me?
Yes, we can hear you.
Yes. Okay. Yeah. Perfect. Because yeah, I minimize all the windows so I cannot see the reactions to make sure that, yeah. Okay. So a quick reality check here. Because of the nature of the industry, because as you know, it's something new. When it was the first quantum computer hardware, for example, the prototype went alive. It's probably in 2010s or something. That's not a lot, for something this consequential. So this means that the industry, especially in Europe and the UK, this is the same also with the US, relies heavily on government subsidies, and it's highly R&D which means that a lot of things are still like in terms of technology readiness level, they're not that developed, in terms of commercial viability at the moment. Despite the hype that you hear, we can touch that on the Q&As because there is a lot of hype out there. If you listen to it, you will think that quantum computing technology readiness level is at the same thing as what the other industries are, like AI industry, for example, which is not the case. So what this means in terms of talent, if say you are a very, you are from outside these big centers, these hubs, like the UK, Europe, or the US. If you are very talented, say you are in Mexico or other parts, it makes it very hard, really, the barrier in terms of being hired. Because, for example, in the UK, from my experience, and I know this is a fact, a lot of government-funded grants come with the condition that you have to hire someone local. And if you cannot hire local people from the residing in the country, this is what, when I say local, it doesn't mean like it has to be someone of a specific nationality. Say for example, you are in the UK, it doesn't have to be a British person as long as they live in the UK. Okay. So this basically makes it one of the things that makes it harder for companies to hire talent, from outside, say, from developing countries. I've done this talk before to a community a quantum computing community in sub-Saharan Africa. One of the complaints that people were, bringing up is that the lack of opportunity to work for like, companies, despite feeling that they have the talent, they have the skills to do that. Well, this is one of the limitations, because, a lot of the money subsidies, really is from the government, and they do impose priorities so that, they can foster local economic growth. Now, this doesn't mean that they cannot hire abroad. This is very often they do that, but that means that, you have to be really good. You have to really be outstanding compared to the local talent that they have in order to go through all the hassle of justifying why they have to hire you versus some other person doing a PhD in, say, Cambridge or Oxford. Okay, so that's the thing. So now I'll go to the thing quickly. My unsolicited advice, if you want to come in. This is, again, when I'm saying this is my personal view, okay? One of the things that I really think you should do if you want to come into industry, or at least be hired by a company like our company, is to try to avoid what I call the generalist trap. So don't try to target every technical role in quantum computing in order to make you like, this will make you like basically spread very thin, okay? Being generalist is okay when you are learning. That's perfect. You want to experiment with different parts of the industry of the field, right? You want to do maybe study error correction, and then you want to do machine learning, quantum machine learning, and so on. That's okay for exploring. But when it comes to actually, you really want to go and work for a company, I think you should probably spend some time, to prepare for like some niche, develop some niche focus, so you can basically dig deeper and develop the deeper knowledge that a generalist doesn't have. So this is also a byproduct of quantum computing being very, very new industry. For example, in web technologies, web development, web technologies have been here. They are well established, mature, and these things. So, well, it's okay if you are a full stack developer. You can do a bit of back end and the front end. You'll probably find a job and these things. But for a field like on quantum computing, where the abstractions haven't been built yet, they're being built as we speak, as I speak here. Nothing is mature, and we are not even sure which frameworks that today will be available tomorrow. Maybe today Qiskit or Penny-Lane, they are popular. Well, it might be in 3 or 5 years they are no longer used. Something else shows up. Okay, so but nevertheless, focus on a thing. I would say, if you want to go into industry, especially find a job in like a company, it would be nice to you give yourself a best chance to focus, to narrow your focus. The other thing, this is mostly for those coming from programming background. Don't assume, just learning about, the using tools, like the tools that I mentioned, Qiskit and these things, they are just enough for you. You need to really have other qualities, if you are like, you want to have like some sort of a research-oriented opportunity in the industry, then two of the things that are very important are like independent thinking, being able to think outside box, being able to have like some sort of a self-initiative, so you're not like showing up and just, people have to give you ideas or give you, a direction, especially for startups. If you want to work for startups where everything moves fast, you need to hit the ground running. These are very, very, very high qualities. And of course, being team player is also critical. Collaboration. The other thing, this is most likely one of the things that I see a lot on social. This is also something I advise the other quantum group is I often see people participate in IBM challenges and they scored 100 or something, okay, that's okay. If you want to work for IBM, that's all right. But I would avoid just, the trap of just highlighting scores. Instead, focus on like practical projects. Build something interesting that a company might be interested in getting you, opening an opportunity for you. Rather than a piece of paper saying you scored whatever in whatever challenge. The other thing is I'm trying to so we can discussion at the end on any points. So the other thing, I see a sign that my internet connection is unstable. Am I still with you? Am I still with you?
We are losing you, Bambordé.
Yeah. Can you hear me now?
Yes.
Yeah. Okay. Did you miss me in any of the other slides?
Well, we saw the beginning of slide of 0400 rejection with grace.
Okay. Okay. Yeah. So I'll only 3 more to go. Then we are done, so we can take questions. Yeah. Yeah. So one of the things that I was saying is that if you get rejected in a company, take it as an opportunity to like. To reflect and be able to, grow from that experience, ask for feedback if possible, and use the experience to fuel your determination, okay? So do not say, for example, I see some people post, oh, I applied for company XYZ, they rejected me. This doesn't help you, and it might actually imply that the company has rejected you because for whatever reason, so that's not it doesn't reflect good. The other thing I would also advise, I see this a lot when I interview people, is acknowledge teamwork. So avoid solo credit, especially if you work with someone else on some project. Always make sure that, okay, this was a project that I did with the person X, Y, Z, and this is what I did, okay? Because this is very, very important as well. Social media presence. I see a lot of people saying they have how many thousands of followers, and yet no quantum company wants to hire them. Well, that's because nobody will hire just for like social media following, right? First of all, how do the companies measure that the people following you are valuable to the company? It's really very hard. So, and also many companies, especially in quantum, because some companies work with government, they tend to avoid like PR type of PR controversies. So that's so instead you should focus on like technical and soft skills. That's what you should focus on. The other thing, this is very important, avoid industry hype. In particular, I would say if you see someone like an academic who has a company sharing something that you think is a hype, do not comment, do not share. Just by commenting and sharing, it doesn't mean that they will hire you. Other people will do the same who have no clue what the result that they are hyping is about, and it makes you look bad as well for other companies who might want to open opportunity for you. This is also this is connected to social media. Is avoid megaphone activism. If you are an old guy like me, already established, it's okay. I sometimes do political rants on LinkedIn because I'm not looking to work for any other company. So, but for you in your early stages, be very careful about, especially in quantum, because as I said, a lot of these quantum computing companies generally work with the government. So if a government has a particular, political thing that you don't like and you start to broadcast that on the socials, that's basically closing you to any other quantum computing company working with that government. So be aware of that. This is the other thing is, this is also related to something I already said about tooling. Don't assume just programming skills are the only thing. You need to build also other foundations. In particular, I'm biased here. Mathematical foundations are very, very important, here. And for that as well, for those of you who are here, I'm happy to give you access to Quantum Formalism Academy. Just email me and we can discuss the logistics for those of you who are interested. The only thing we ask is you have to have commitment to commit at least 5 hours per week to go into our program. Okay, so it's not like just log in and mess about. We have like a structured program, and for those of you here on the audience who are interested in this, just feel free to email me. Yeah, we can sort some about. Okay, it's, are you still with me? I hope I haven't cut. This is the final slide.
Okay, thank you. I think we're about to lose you again. After you said the 5 hours per week, that was an interesting part.
Yeah, well, we can get that on the question and answers. Yeah, but this is the final thing that I want to make is that ignore what I said, in a way, it might sound like contradicting, but at the end of the day, have confidence in your ability, be willing to put on the hard work and, make the decisions for yourself. You can take advice like what I was saying or other people's advice, but at the end of the day, you have to make your own decision. You know exactly what is right for you. So that's it. So here's my email. For those of you who want to reach out, feel free to reach out to me. Hopefully, after I stop sharing, the connection will be better because of the bandwidth, and maybe I can take questions or whatever clarification to some of the stuff that I went through. So sorry again for the for the connection. It happened in the wrong time. So that's it from me. Thank you so much for listening.
Thank you. Thank you very much, Bambordé. I think you're going to receive hundreds of emails.
Okay, that's okay. Yeah, I might not be able to reply. So I was saying you need to have, if you want to join that quantum formalism, to go through our program. Okay, so when you email, we will have a call with you to see when can you start and do you have time. So my advice is don't email me until you know you have 5 hours per week. You can email me anytime. Just remind me that you came from here.
That's an easy requirement, only 5 hours per week.
Yeah.
Okay, so we're ready for a couple of questions, if you agree, Bambordé. Okay.
Yes, I am. Okay. I'm ready. Let me stop this. Hopefully the bandwidth.
Are there any questions inside the auditorium? Because we have 2 questions on Discord. Okay. Hold on a second. Don't start talking.
Thank you very much for your presentation and for all your advices. And I have a question relative with your last advices. You start this list of advices saying that it's important to choose a niche, and I think that these decisions could be a little hard in the sense that if we are recently introducing in this field, we don't know or we don't have many information about which niche are the most popular or the most demand. For example, in the field of quantum algorithms. So which advice could you provide us in order to find more information about these kind of niches?
Yeah, I actually had a nice diagram. I forgot to include it, where you have different layers of the quantum stack that tells you. Let's see if I can find it. But otherwise, I can include it on the slide and email you. But what I would say is, I completely understand when you are getting started first. Obviously, this is a learning phase. You don't know much about the different moving parts of the quantum computing stack. Mostly you hear about applications. People talk about algorithms, but there are other things also that are very important. Especially closer to the hardware, like control, for instance. To all the way up to like stuff like error correction. This type of stuff. These are all like specialized parts of the quantum stack that traditionally only like maybe people who did a PhD or something that do this, but it's also feasible with the right background, with the right attitude to learn and be able to get into these things, because they don't have much competition compared to applications. Everyone wants to do applications. That's the problem. You have thousands or millions of people who get started with application. They want to all work on application, but the applications will be useless if the things underneath, if you can't handle the noise, you can't, the other things be invisible to the normal users, are not properly developed. Yeah, so I guess I don't have a concrete answer, but I would say, try to explore. I think the best thing to start is actually, you can Google, there's something called quantum computing stack. This image I forgot to include in our slide. It has all the different layers of the ecosystem, from the hardware to the application, and then you can find a niche. And very often, depending on where you are right now, your background, one of the niches can be very close to you. Maybe you might have to learn something a little bit more in order to get into it. Yeah.
Thanks for your advice, and best successful for your research. Thanks.
Thank you.
Otra pregunta, another question here.
Not here? Oh, well, we switch to the Discord question.
En español y la traducimos con gusto, ¿eh?
Okay, I'm going to read one of the questions that came up in Discord. This is from Flor Maria. She says, some technologies like AI are developing faster than some humans' ability to understand and give them a meaningful use. What is your view about this take? Do you think quantum computing will follow the same path as the AI hyping these days? Do you have any advice to keep ourselves competitive?
Yeah, that's a very interesting question. There is obviously the danger of following the same. The good thing with the quantum computing, this is where also I would say there is an opportunity for people who want to come into this field who are outside these the traditional hubs, like in Europe, in the US, is that there are very few algorithms. If you remove the hype, every week you see a paper saying they have a quantum advantage, but then when you look, when you read a little bit closer, it says it paves the way. They use the word could pave the way to quantum advantage. So it's actually not, because we don't have the devices yet. So there is an opportunity to find applications that maybe we haven't thought about. One of the things that in my point of view, is a lot of people, we are wasting a lot of time thinking about existing applications, like things that we know, to try to fit it into quantum. Stuff like portfolio optimization and all this type of stuff. In fact, I was talking to someone. I said to them, if somebody said right now they have a portfolio, an algorithm, a quantum algorithm that gives them an alpha in their investment, then they shouldn't sell the algorithm. They should create a hedge fund. So long story short, I think there is a risk, of course, that the hype that we see in terms of capability will not, meet up to the reality that we have right now. So we don't have the hardware yet to really be able to run, the algorithms that provide us the advantage that we know classically we cannot do. So yeah.
Another question from Vic. About your proposal of zero knowledge proof, could you give us some practical examples or ideas of how it could be performed?
I would need some mathematics, but maybe. Well, if you come to Quantum Formalism Academy, we can definitely put you on the thing. But in the context of quantum computing, for example, say, for example, I have an algorithm, for instance. I say, let's see. Say I have an optimization algorithm. I say to you that this optimization algorithm is the best. It does whatever better than the non-classical existing classical algorithm that we know of. And here are the benchmarks. I've done the benchmarks on non-trivial data, on this and these things, but I don't want to share my algorithm with you. So in this case, you could use the zero knowledge proof. You could, me as a prover, maybe I should share the slide again. It's much more easier to convey this idea, this use case, without going too much into the details. Can you see this?
It's charging.
Not yet. Yeah, we can see it.
Okay, so in this case, you have like, I'm the prover. Okay, I want to prove you that my optimization algorithm does have some sort of advantage. Okay, so in that case, I built a zero knowledge proof protocol to extract the proof of my advantage, that the performance, it did whatever I said to you, I promised to you. And then we have you as a person, who want to buy my algorithm, you are able to verify. So you are the verifier. So a zero algorithm, generally you have a prover, the zero knowledge proof protocol, and then you have a verifier to verify that what has been claimed is true. So I'm able to prove without giving the details. Yeah. So, and there are obviously for any algorithm, you can, the opportunity I'm saying with this is you can try to do this with any interesting algorithm that someone tries to sell to you, or you yourself you want to develop, and you don't want to share the details with someone else. You want to keep it secret, but you can prove the properties of the algorithm without disclosing the exact construction, so that someone doesn't copy you.
Thank you so much for that answer, Bam. Next one comes from Guillermo Ramirez. How do you envision the development of quantum computing in the Latin American context? Can any of the Latin American nations be considered as a spearhead?
Yeah, this is very interesting. It's unfortunately at the moment, it's implicit in your question, and I also mentioned this in during the presentation. Most of the development right now is happening in the developed countries, like in Europe, in the UK. Well, UK is also Europe. When I say Europe, I say European Union. in the US, Canada, all these. Unfortunately, in the other developed, in other countries, like in Latin America, there hasn't been that much effort. This also limits the opportunity for talented young people like yourself, to be able to contribute without having to leave and going overseas, to go and. But so I think this there is definitely a need for to have some sort of a national program, so the governments in the Latin American countries, maybe I would rather than having individual programs, maybe they could have something like some sort of a collaborative type of program, including all the Latin American companies. So there is money, everyone putting in money to invest in a program that the researchers across the countries being part of it can participate and share knowledge and build capabilities in Latin America. Yeah, because otherwise what's happening is, we are unfortunately, what happens is you might end up having brain drain. Most of the talented researchers and professionals end up going to coming to Europe, US, and others. So that means that Latin America is left a little bit behind, become like a follower, an importer of the technology as opposed to builder. So yeah, so I think I would like to see more government programs, and maybe in the bigger countries, in anything like I would say like Brazil, for instance, and other bigger countries, Mexico, maybe you could come together and create some sort of consortia, that could help people in the continent. Yeah.
Thank you so much, Bambordé. I think we have space for one or two questions more.
I have a question here, Victor. Yeah, I have a question myself, Bambordé, related to the first part of your presentation. One of the problems when you try to solve real-world problems with quantum algorithms is how to map a real variables, continuous variables of real problems to qubits to start doing some quantum algorithm. And some of us have as a research area, for instance, image processing. And in image processing, you have lots of pixels, and each pixel has to be represented with in classical form with 8 bits, for instance. And when you come up with a solution to map all those information to qubits to start thinking about quantum algorithms, you find out that you need lots of qubits, hundreds of qubits that actual or present time quantum computers don't have. So the representation of this information in qubits is a real problem. Do you have any do you know of any advancement on this field?
Yeah, one thing you could. It's also related to the geometry, to the thing that I was saying before. I can follow up. We actually did some things on this. For example, where you take advantage of the symmetry of the data in order to help you with your embedding. So the model doesn't need to learn everything. So it's just it takes advantage of the natural symmetry of the classical data. So there's something called equivariant embeddings. Maybe I'll follow up with you. We found it to be very, very interesting, especially for image type of problems, or even for DNA, things that are like high dimensional stuff, to use to make the natural symmetry present in the classical data itself to help you with the embeddings. I can follow up with this video with some references. There are some interesting indications that this could be symmetry-aware embeddings could help for this type of problems.
Oh, thank you. Sounds like a good idea. Thank you.
Last question, Bambordé. Here we go. Thank you for sharing your high-level vision. For those of us eager to dig deeper into the mathematical foundations of architecture behind this approach, what core preprints or upcoming technical milestones should we follow to see these concepts in action?
Ooh. Well, I would start with, from a mathematical point of view, I would definitely start, first of all, I think most of you have a basic linear algebra thing. That's very good to have. Group theory is important. A lot of people underestimate the importance of group theory, but a lot of the things, the properties that you have, the unitary with the quantum gates, they are like a manifestation of the group theoretic properties of them, or in fact, even beyond that is Lie theory. So you need to understand, learn the topology, manifold theory, and then Lie theory. You should be able, at least from an algorithmic point of view, be able to really be working, like reading papers at the frontier, and be able to perhaps contribute in a more meaningful way than if you don't have these. You're not equipped with these mathematical toolkits, because then you are not able to see. There's a lot of properties that are hidden to you because you don't have the mathematical lenses to see that. Yeah. So, yeah.
Okay, thank you very much for those answers, Bambordé. I give the floor to Dr. Boris Escalante to close this session.
Well, Bambordé, it's been a very interesting and enlightening conference. Thank you very much. As you saw, there are many people triggered by all that you told us today. I really hope we can keep in touch with all these ideas that you presented to us. And I thank you again on behalf of everyone here at the auditorium and the hundreds of people who are online. I think we have more than 700 people online. So on behalf of everyone, we thank you again and hope to keep in contact with you. Thank you very much, Bambordé. Bambordé.
Connections. I think I need to go and drink. Thank you so much. Yeah, sorry for the connection. Yeah. So, yeah. Have a great day, everyone.
You are receiving a big applause, Bambordé. Thank you very much.
Thank you.
Bye-bye. Thank you.
Bye.